Okay, next we're going to learn some basic for formulas derivation. Okay, the understanding for mass balance. Now, when you prepare a chemical, let's say 0.20 moles, or molo, with moles. At the time, the typing was confusing. Okay, if you prepare 0.2 moles of HA and dilute it to 1 liter, sure, then you say that analytical concentration for that chemical is this value, okay, that many moles per liter. But then what happened in the solution? Some of the HA will ionize. So for those that ionize, then you will get these ions. So the degree of ionization will depend on the Ka. So the ionization indicate, these two concentrations will be the same, and they come from 1 molecule of HA. So you get 2 ions from 1 molecule. So now, as you can envision, the total concentration being 0.2, but the distribution will be between 2 types of HA. One type will be those HA will ionize according to that. Okay, plus those they don't want to ionize, they just stay as HA. Okay, so there will be only 2 possibilities for the HA. So now you can write this is the total is equal to those ionized will be uniquely represented by the A minus, right? So notice here, so the A minus, when this is ionized, and you get numerically the same of A minus, right? X is equal to X. So this represents the quantity of that ionized. Now for those that are not ionized, then we can keep the original formula, okay, as HA. So the sum of these 2 concentrations is equal to that. And this is your mass balance, okay, based on the quantity, mass quantity. Okay, so this is for HA formula. Now this can be extrapolated into higher formula, such as H2A. Okay, then let's say you measure H2A quantity is equal to 0.2. Now the 0.2 total will be distributed amongst those that not ionized at all, those ionized just once, and those ionized uniquely twice. Okay, so remember, this is how you write mass balance expression. Okay, so what's the big deal to do this? Well, used for formulas derivation. Now, another one is called charge balance. So based on charge. So in a solution, you're going to have plus ions as well as minus ions. Then in a neutral, in one solution, then the total charge, the total plus charge must be equal to the total negative charge because the whole charge is neutral. So you can prove that by putting your finger into pure water, you don't get an electrical shock. Or sodium chloride solution, then you put your finger in, you don't get an electrical shock because it is neutral, okay? So what it amounts to, the sum of plus charges must be equal to the sum of negative charges, okay? So that is charge balance. Now notice, in pure water to begin with, pure water, you have 10 to the minus 7 of the cation as well as the anion. And they just balance out because they are exactly equal, so it is balanced. So they are equal. Now, what about when you dissolve NaCl into water, then you get cations and anion in addition to the original proton from water. Okay, so for charge balance, correctly written will be the water proton plus the sodium cation on one side. So the sum of the two is the total plus charge, and then a negative charge will be this one from water and this one from NaCl, obviously. So now it's balanced form, okay, balance. Now, if you incorporate a quantity, let's say you prepare 0.1 molar NaCl, then for mass balance, then you will get 0.1 molar sodium ion and 0.1 molar chloride anion. Okay, let's look into something more complicated formula, okay? Instead of dissolving NaCl, we dissolve sodium phosphate, then you better know the formula will be like this, okay? So dissolve into water, the total quantity. Now, for mass balance, for the sodium cation, then you will realize that because the whole formula you prepare for is 0.2 molar. This stands for the whole formula. So if you kick in the individual ion, then the sodium cation, the concentration is 0.6. Okay, keep that in mind, it's 0.6. Now, for the phosphate, it is 0.2. Yep, it is 0.2. But then for the anion, it's going to be reaction. Okay, so this exists as its own ion formula, but then you can associate with the proton in water because this is dissolved into water, so you have H plus available in water, so it will associate once. Okay, then those could associate 2 times, so you will get this formula and until go to the end. So we can see that the distribution for the phosphate will be more or less. More or less. Nonetheless, you have all these species in a mixture containing the phosphate anion. So now this is your mass balance. The total mass of phosphate will be equal to the sum of all these species. Okay? So this is a mass balance. Be sure you know how to write this. Now, charge balance, we are looking at the charge contribution from each chemical. So contribution of charge. So positive ions on one side, so sodium, you get just sodium, 1 charge, so the contribution from the concentration is 1 charge, so you multiply by 1. Then here is 1 charge multiplied by 1 as well. Then it's balanced for the negative anion, so hydroxide automatically there, okay? So the hydroxide, negative 1 contribution. Now be careful with the phosphate. Notice this represents concentration. But then for charge number, then you need to extract the charge because it's 3 minus, so the charge contribution is 3 times this concentration. Okay, remember it's the charge contribution. Okay, you have a concentration now, then what is the contribution for that? Well, it's 3 times the concentration. Okay, memorize that. And here, for this species, then it's 2 times. Oh, sorry, the 2 should be extracted to the outside in front of the concentration. Okay, so be sure this is in front, multiply the concentration. Then here, then 1 multiply this guy. Now, the H3PO4 is neutral, so it doesn't contribute to the charge balance. So remember that you don't include this guy in it. Any question with that? Okay.